Hello. In this session, we are going to introduce you to the sensors. Before we go deeper, let me tell you something very clearly. The sensors are like the heart, kidney, liver for any IoT project. So, we need to learn in depth about the sensors before we go into any implementation. Choosing the right sensor, selecting the appropriate sensor out of multiple available sensors, choosing the best one, in short, is the most important thing that we need to learn. In this session, the listener can get a clear idea of what sensors are all about, why do we need them, contrast between industrial and day-to-day sensors, different type of signals used in Arduino board, contrast between the analog and digital sensors. Let's get into the types of sensors. What is a sensor? Sensors are electrical or mechanical components that can sense required parameters like humidity, turbidity of a fluid, temperature, pressure, velocity, etc. To make it very precise, your body has got numerous sensors. When somebody touches you, you sense it. That is it. Sensor is all about sensing. In IoT, a sensor is chosen based on the signal to be sensed, whether it is analog or digital. Sensors can be classified as multiple categories, which include biomedical sensors, mechanical sensors, force pressure sensors. Biomedical sensors can include pulse sensor, brainwave sensor, etc. All these come under biomedical and they are used in medical applications. Mechanical sensor can include rotary sensor, tilt sensor, gyro sensor. The force or pressure sensors include piezo sensors, force sensitive resistors, etc. We have presented the pictorial representation of pulse sensor, force sensor, and 6-axis gyro sensor for your reference in front. Industrial and day-to-day sensors. What can be classified as industrial sensor? What could be classified as a simple day-to-day sensor? Industrial sensors are very simple, yet they are perfect and powerful. Manufacturing all the industrial sensors is mainly aimed towards achieving higher rigidity and accuracy. It is all about increased accuracy and stability. An error of order 10 to the power minus 3 also cannot be tolerated in industry sensors because they might be controlling a real time application which must be monitored with 100% accuracy. In that case, the errors are to be 100% curtailed. Day to day sensors are not seen for their rigidity or higher accuracy. There can be mild changes here and there with respect to the measurement. They are mostly manufactured for prototyping with microcontrollers like Arduino, NodeMCU, STM32, etc. It is acceptable to have a slight error rate in such sensors, and one important point to be highlighted here, the industrial sensors could be expensive where the day-to-day IR sensor or whatever sensor we use could be cheaper. In the slide right now, you are seeing an industry standard IR sensor, whereas the day-to-day used IR sensor is also presented. We in our entire video series have used the day-to-day usable sensors because it is available in abundant in the market and they are affordable. For learning, for prototyping, we will go with day-to-day usable sensors where when you deploy it in the industry, you need to go with higher grade industry standard sensors. We need to understand the types of signals before we go deeper. There are two categories, analog and digital signals. Analog signals are continuous in nature. The flowing stream of a river should be taken as an example for analog signal. These signals can have any value. It is not solid like 0 or 1. It could be anywhere in between. You can see the analog signal representation we have presented in front of you. It is just like a flow of water, which means it can be anywhere with respect to the value. Coming to the digital signals, they are discrete in nature. They vary around only limited values. In electronics, most of the digital signals, I can say that almost every digital signal is represented as 1 or 0. The digital clock shows time only in digits, which is a typical example for digital signal. You can see the digital signal presented here. It has to be 0 or 1. It cannot be like analog signals. Analog versus digital signals should further be taken to the next level. Which signal is easy to process and store? As most of the signals found in nature are analog signals, including the voice that I am giving you right now is analog initially. Can we use analog signals all the time as they are pure and reduce the need for processing? This is a very good question. No, we cannot use analog signal all the time. As these signals are continuous in nature, processing these signals is very hard and time consuming. Also, it requires high storage space. By the time the current value is being processed and stored, the signal really progresses in time. So there is a chance and a high risk of missing multiple values in future. When compared to the analog signals, digital signals are easy to store and can be processed much easily. Also, we are dealing with a limited number of values, which is mostly zeros and ones. Hence, it is always preferred to go with processing digital signals over analog signals. Interconversion is one thing that we need to understand how exactly it happens. Conversion from one type of signal to another type is much needed as most of the signals in nature are analog. But the processing has to be done as digital. Converting the analog to digital signal is possible, but digital to analog conversion is not possible. In IoT microcontrollers like Arduino, Node MCU, analog to digital conversion is done using ADC techniques. I have an analog value. I need to use ADC on board. I'll convert it to digital value. That's very simple. The ADC helps you to convert analog values to digital values. We need to understand about analog and digital sensors. As the signals are of two types, similarly, the sensors are also of two types, analog sensors and digital sensors. The output signal from analog sensors are continuous in nature. For instance, consider a force sensor which continuously output different values depending on the force applied on it, which means I am punching the sensor with a hard intensity, it will give me a different value. I am just touching the sensor, it will give me a lower value. Coming to the digital sensors, the output from the sensors are either high or low. It is similar to yes or no, which is 0 or 1. Consider an IR sensor. If an obstacle is found in front, it will say yes, else it will say no, which is replicated through high or low indication. It is like alive or dead. It cannot be intermediate. Thank you. In this session, we will understand the type of analog and digital sensors. After listening to this session, you will have a clear idea about the types of analog sensors, the types of digital sensors, concept of signal sampling, and you will understand the fundamentals of ADC and DAC, which is nothing but analog to digital converters and digital to analog converters. Let's first start with analog digital sensors and then we will navigate to ADC and DAC conversions. Types of analog sensors. As we are familiar with the term sensor and types of sensors, analog and digital, we need to now go a step ahead. Most of the sensors that we use are analog sensors. A table is presented in front of you which has got some set of analog sensors which are quite frequently used with the purpose. LDR is the first in the list that we have referred. LDR is nothing but light dependent resistor. It is used to sense the intensity of the light in the surroundings. Ultrasonic sound sensor comes second in the list. It is used to measure the distance of the obstacles. We use this mostly in the parking applications. Force sensitive resistors comes third. This is used to measure the impact or the force given onto a surface. Gyroscope sensor comes finally in the list. It is used to measure the tilts and the angle at which the surface is placed. Types of digital sensors. Digital sensors are used to know whether a desired process is happening or not. For example, we use a digital sensor if you want to know whether an obstacle is present or not. It will say as yes or no. It is all binary in terms of results. To know how far the obstacle is, we have to use an analog sensor because the output value which we get is corresponding to the distance. But on the other hand, if you want to know if an obstacle is present or not, we will go with digital sensor. If you want to know the distance, it has to be analog because it varies. If you want to know if it is present or not, you need to go with digital because it tells you if it is available or not. We will have a fundamental set of sensors displayed in front of you on the table, and we will also see for what it is used. The first in the list is IR sensor, which is nothing but infrared sensor. This is used to sense the obstacles within a limited radius of distance. Hall effect sensor. It is used to detect the presence of the magnetic field. Touch switches to make touchscreen switchboards for operating electronic appliances. Gas sensor to detect the presence of gases like LPG for fire detection kind of applications. Whatever we have presented here is only a very limited set of sensors for your fundamental understanding. There are so many other digital and analog sensors available in the market. We request you to go through it if you want to know more about it. Now we got to learn about sampling. Sampling a signal is very important, and next few minutes we are going to talk about it. Sampling is the commonly used term in analog to digital conversion. The process of converting an analog to digital signal is done using the sampling process. In this process, we use auxiliary clock or high frequency signal. To understand this concept better, we need to consider an instance. You are going to listen to a fast music which can be considered a rap song, and you are requested to note down the lyrics of that song. So how do you do? Step 1. Play the song. It is same as recording the input from some analog sensor. Step 2. Pause the song after listening to few words or word. Introducing a high frequency clock signal can be related here. Step 3. Note down the word and replay the song. Here it is equivalent to save the sample and continue the sampling. So it is as good as you understanding the lyric and then making a note of it. You can't do it continuously. So what do we do is we play it step by step, and that's what is called sampling. The same is represented diagrammatically in the picture that you are seeing right in front. Once this process is done, you now have various discrete words which when joined together gives you back the literal lyric of the song. Similarly, when all the digital samples are joined back, they almost give back the original input analog signal, and that's what you are seeing in front of you in an animated pattern. A signal is sampled by taking certain points on the analog signal instead of remembering the whole signal such that the wave can be reconstructed. The task of sample collection is done by an externally applied digital clock signal or a high frequency signal. The same is diagrammatically represented as an animation in front of you for you to understand things better. The analog signal is exactly reconstructed to the utmost accuracy possible through this sampling process. That is it, and this is the fundamental for everything that you are going to learn in the near future. ADC using thresholding. Analog to digital conversion can also be done through thresholding technique. This is the easiest and effective type of ADC. It is used when you want the output to oscillate only between two values. For instance, you are asked to look at a rotating giant wheel and you are asked to write down 1 in a notepad when the giant wheel crosses a particular point. If not, you must note down 0, which means you should track the position of the giant wheel in order to get an output. Similarly, a threshold will be set, and when the input of the analog signal goes above this value, we output it as a 1 or 0, which means that we have converted the analog signal to a digital signal. The analog signal can be varying, but we connect it to either 0 or 1 easily. The same has been represented in the picture that you see in front of you. It has got on or off, which is corresponding to 1 or 0. The analog signal can vary, but we are equating it to the digital signal conversion easily through this thresholding process. We need to learn about digital to analog conversion. We have now seen the analog to digital conversion. Is it as easy to convert digital back to analog signals? The answer is really no. Although the process of DAC conversion still exists, there is no certainty in bringing back the sampled analog signal. It is very challenging. The process of digital to analog conversion is very hard as well as expensive in order to get a higher resolution analog signal. Here are some of the industrial standard DACs used across many places which are presented in front of you. It must be noted that in this entire lecture series, we are not using any applications with DAC as it is difficult and it might not get us the 100% accuracy that we want. We stay with ADCs. Thank you. Friends, in this session, we will understand interfacing analog sensors with Arduino board. We will also take a couple of exercises that can help you in understanding this pretty clearly. After the session, you will understand how do you interface analog sensors with Arduino Uno, what an LDR is all about, how does it work, how can someone interface LDR with Arduino Uno, what is FSR and how to interface FSR with Arduino Uno. All these are covered in this session. Stay tuned. Let's go into the fundamental interfacing exercises. Before that, we need to understand how exactly the Arduino supports for analog sensor interfacing process. The Arduino Uno uses Atmega 328P microcontroller which has many type of input pins like digital input, analog input, I2C, SPI and UART. To interface analog devices like LDR, FSR to the Arduino, analog pins must be used. You can see in front of you there is a red circled highlighted thing is present and that is called analog in pins. These pins are connected internally to an ADC which converts the input analog data to digital bits and stores in memory for further processing. Let's get into LDR interfacing exercise. We have learned enough about the analog and digital sensors theoretically. Now it is time for us to turn the theory to the practicals. LDR is acronym of light dependent resistor, which is an analog output sensor which can measure the intensity of the light around it. Now, using this LDR, we are going to build a project. You are given a task to monitor and to control the lighting required for the plants to grow properly inside a greenhouse. You are presented with a type of LDR in front of you as a pictorial representation. Before we go into the implementation, we need to understand how exactly LDR works. The working of LDR is very simple. It consists of a copper winding present on the top of it, which is typically a conducting material and sensitive to photoelectrons. When the light is projected onto this material, it causes the electrons to excite and reach an higher energy level. Thereby, it allows the electric current to pass through the LDR. This current is proportional to the amount of light intensity which is applied onto the sensor. You can see an animation which helps you in understanding the process in front of you. Let's start the interfacing process. For that, you need to go through this connection diagram clearly. The Arduino, LDR, resistor and LEDs are the components which are used here, and we have used breadboard and the connections are revealed in front of you. Arduino's 5V pin has to be connected to LDR's pin 1. Arduino's A1, which is analog 1, is connected to LDR's pin 2, also to pin 1 of resistor. You can see the way we have connected using the breadboard. Arduino's pin 7 is connected to LED's positive. Arduino's ground is connected to resistor's pin 2 and LED's negative pin. That is it. But one more important thing to be understood here. LDR is a resistance based device. Hence, it doesn't have any polarity, which means you need not worry about which side to be connected to which pin. A resistor of range 10 kilo ohm to 100 kilo ohms can be used as a current limiting resistor. A current limiting resistor is used in this circuit in order to protect excess current from getting into the input pins of the Arduino board. Please note that the input pins of Arduino are tolerant to a maximum current of approximately 40 milliamps and an excess current could certainly damage the pins. It is time to code it right now. Please go through the code that is presented in front of you. As told prior, we are going to design a greenhouse. The plants are grown using artificial lighting. If enough light is not present, we need to apply light onto it so that the plants can grow better. In order to check the lighting inside the greenhouse, we will be using an LDR sensor. If the intensity of the sunlight goes down, we need to turn on the light which is connected to digital pin 7 of Arduino. LDR is connected to analog pin A1 of Arduino Uno and its value is stored in the sensor value variable. You can see all this as code right in front of you. The sensor pin is assigned with A1, sensor value is initialized to 0, light is with 7, which means that it is supplying the artificial light. We will go to the next part of the code where we are setting up the baud rate initially. The baud rate is set up to 9600 and it has to be consistently set up with the serial monitor also for you to see the results. As we get input from the LDR, we have to declare analog pin A1 as an input port. From the digital pin 7, we get output light. So we have to declare digital pin as the output port. All these have been done in the code and you can see it right in front of you. Coming to the loop part of it, the sensor value stores the LDR value which is consistently read from the A1 pin. If this value is less than 700, we can understand that the lighting is not sufficient and we got to provide an additional external lighting source through the LED which we have connected on pin number 7. If the reading is above 700, we need not bother as we understand sufficient lighting is present for the plant to grow. The coding reveals the same. The sensor value is assigned to analog read of sensor pin, which means that it continuously reads that value. If this value is less than 700, we glow the LED. If otherwise, we do not glow the LED because we have sufficient lighting. The entire process is demonstrated right now practically for your easier understanding. Here you can see the real-time interfacing with Arduino board. We have used the same connection details as we have presented you during the presentation earlier. The same connection details have been followed and now it is all set to go. Now we have to upload the code after validation. So the uploading happens right now in front of you and once it is uploaded, you can see the complete demo live up and running. The uploading has happened right now and you can see that the LED is glowing properly, which means there is no sufficient light available here, so LED is glowing. Once we impact with the light on the LDR, you can see that the LED stopped glowing. This is very simple exercise, yet a very powerful exercise to understand the usage of LDR. When more light is impacted on the LDR, the LED will switch off. When there is no light, the LED will switch on. Now, we got to go to the next sensor. It is nothing but force sensitive resistor. It is very useful in the industry as well as in the prototyping applications that we are building to understand the amount of force applied onto a surface. This time you are assigned with a task to build a digital weighing machine. The basic functionality of these machines lie in measuring the weight, which is nothing but the force applied onto the weighing plate. FSR is nothing but force sensitive resistor. It is a scaled down version of industrial strain gauges and this is the reason why their accuracy is very high for real-time applications. We have presented you the image of force sensitive resistor in front of you to understand how it looks like. FSR's fundamental working principle is very easy and it is very important for you to understand it. FSR works under the principle of change in area which can cause a change in the resistance of the material, thereby causing a variable current to pass through it. To make it simple, the surface of the sensor consists of a copper film which is sensitive to the pressure changes and instantly changes the area of the sensor when a force is applied. When a force is applied on this film, it causes a change in the area of the plate. According to the formula which you are seeing in front of you, when the area increases, the resistance decreases, thereby increasing the current. This change in current is proportional to the weight placed on the plate. If the area increases, then the resistance decreases, thereby the current increases. That's what the formula reveals. The connections are very simple and you can see the connection diagram which is presented in front of you. Arduino's 5-volt pin is connected to FSR's pin 1. Arduino's A5 pin is connected to FSR's pin 2 and also to the resistor's pin 1. The Arduino's ground is connected to resistor's pin 2. Output from the FSR sensor can be obtained by interfacing the sensor as shown in the figure. Similar to the LDR sensor, FSR is also resistance-based sensor, which means there is no polarity. One of the terminals go to the 5-volt pin of Arduino and other goes to the analog pin A5, and the same terminal is pulled low using a resistor. As discussed, Arduino has a 10-bit ADC, which means that the output value can vary only from the range of 0 to 1023. These values can be used for thresholding. It is time to code it. The FSR sensor's output is connected to the analog pin 5 of Arduino. Weight is the variable that we use to store the FSR reading which we are reading continuously. The same has been reflected in the code. Setup part of it has to be used to set the baud rate, also to set the input port output port details. To begin with the communication, we have set the baud rate as 9600. As we are reading the data from the analog pin 5 to which the FSR is connected, we are declaring the pin as input port. We need to go to the loop part of it. Weight is the variable which consistently is written from the analog read that happens with the FSR pin. If the weight is less than 500, we can understand that the object is not heavy. Else, the object is heavy. Very simple, and you are going to see the demo of the same shortly. Thank you. We are going to demonstrate the FSR interfacing with Arduino. FSR is nothing but force sensitive resistor, and the wiring is all done as we discussed in the earlier presentation. The wiring is simple and you need to follow the same procedure as we have demonstrated you. Now we are going to burn the code after compilation, and it is to be done right now, and once it is done you can see the demo live up and running. Now the process is on, it is uploading, and uploading is all happening. It's done. Now you see that you get a reply as the object is not heavy. What is it? Very simple. You got a force sensitive resistor here. There is no object or no impact given on the force sensitive resistor, and hence you see that the object is not heavy message, which implies that there is no object placed over this force sensitive resistor. Now I am going to give some impact here, which means I am keeping some object here as you can see, and now you will get an immediate message as the object is heavy, which implies that there is some impact or object placed over that force sensitive resistor. That is it. It is very simple. Now I have removed it. You must be seeing the message again as the object is not heavy. That's it. We have interfaced the force sensitive resistor with Arduino. Thank you. In this session, we are going to learn how to interface IR sensor and potentiometer with Arduino through a step-by-step explanation and also with a demo. After listening to this session, the listener will have a clear idea about how IR sensor works and what is it all about. How do we interface IR sensor with Arduino? What a potentiometer is all about and how do we interface it with Arduino? And applications of IR sensor and potentiometer. All these will be covered in this session, and it will be a practical learning in this session. IR sensor and its working. IR sensor is a digital sensor, which means that the output given by the sensor will be a digital value. It can either be 1 or 0. The sensor has two LEDs on it, which are IR emitter and receiver. It keeps transmitting the IR light and receives the same amount of light in the presence of any obstacle in front of it. IR rays are also a form of electromagnetic waves, but why are we not able to see it? The wavelength of IR rays is not present in the region of visible light, and that is the reason. You can see that we have marked it as a circle in front of you. It is not present in the region of visible light, so we cannot see it. Let's get into IR sensor quickly. IR is the acronym for infrared sensor. It basically works on the principle of infrared technology. IR sensor emits a rays continuously, and if any object obstructs the rays, it gets reflected and gets detected by the IR receiver. We have used a pictorial representation for your easier understanding. The rays are getting continuously emitted, and in case an obstacle comes in front, it will be reflected back. And this is received by the IR receiver. This is the simple principle that IR sensor follows. So, what can be the application that we can build using this IR sensor? It is used mostly in obstacle detection, line following robots, etc. Let us now interface this IR sensor with a microcontroller. How do we interface IR sensor? We have got the diagrammatic representation for the connections and you can easily understand it. The VCC of the IR sensor has to be connected to the 5 volts pin of Arduino Uno. The ground of IR sensor has to be connected to ground of Arduino Uno. The output of IR sensor has to be connected to pin number 8 of Arduino Uno. You can choose any other pin also, but make sure you reflect it properly in the coding. And we have diagrammatically represented it for your easier understanding. We need to now code it and the time has come for it. The IR sensor is attached to the pin 8 of Arduino Uno in this connection diagram which we have referred. The variable value is to be first initialized in order to store the output of the IR sensor. Pin mode is used to declare A0 as input port. Serial communication is set at a baud rate of 9600. You can see the code right now. The first line is nothing but IR underscore sensor. It is a variable and we have used pin 8. Here we have initialized. The value is equal to 0. It is again a variable and it is used to store the output of the IR sensor. Getting into the setup, we are setting up the baud rate and the next line we are setting up IR sensor as input port. The IR underscore sensor has been made as input port and it is A0 pin that we are going to use here. We need to now go further into the loop part of the code. In the loop part, you can understand that we have got value is assigned to the digital read of IR sensor. We are using the function digital read here, which will continuously read the input from the IR sensor and assign it to the variable value. If value is equal to 0, then obstacle is detected. Otherwise, the obstacle is not detected and the way is clear. This is simple conditional statement that we have used. If else is sufficient for us to code this and we can intimate the status of presence of an obstacle or not easily. In this tutorial, we will understand how exactly to interface a digital IR sensor with Arduino. You can see that the connections are made as per the instructions that are given during the tutorial. Just follow that meticulously and do the connections. Now you can see that in one of the LEDs on the IR sensor, you get a violet color light coming out. This cannot be seen with naked eyes and this has to be seen through camera for you to realize it because it is IR. Once the connections are all set, we are going to go with the demonstration and the code is available here for you to upload it. And make sure you write the code appropriately and follow the instructions as given by us and go to tools, select the appropriate port and upload the code after compilation. Once it is done, the system is all ready to be tested. We can detect obstacles right now with this system and that's what we are going to demonstrate. Now, please open the serial monitor for you to get a complete output and understanding. You can see that there is nothing as an obstacle is present over the IR, over the sensor, and clear way ahead is the message that has come. Now I'm keeping my hand over it as an obstacle and the obstacle is detected. Obstacles are detected through the IR rays getting interrupted and when I remove hand, clear way ahead has come. Now I keep my hand again, obstacle is detected. That is it. It is a simple system to detect the obstacles with IR sensor and Arduino. We will learn about potentiometer right now. What is a potentiometer? Potentiometer is commonly regarded as pot. It is a variable resistor, which means that the resistance can be changed as per the requirement and we can obtain the variable current based on the movement that we give. Based on the tuning, we can get the variable current is the point. Every potentiometer is predefined with certain value that specifies the maximum value up to which the resistance can be varied. The resistance of the potentiometer shown in the figure can be varied up to a maximum of 1 kilo ohms. Most of the potentiometers used will have a rotary head which can be turned in order to increase or decrease the resistance across the two terminals. We have got two types of potentiometers presented in front of you, rotation type and slide type. Now how does it work? Unlike the standard resistors that we use, the resistance of the material varies proportional to the angle of rotation of the knob. Let's look into the diagram that we have in front of us right now. Based on the movement of the wiper in the resistive track, we get the output. Very simple. When the wiper is moved, the resistance automatically varies. So what are the kind of applications that we can build with potentiometers? Potentiometers can be used in applications like fan regulator, the volume control in electronic devices, the voltage divider in electronic circuits, etc. Now, time has come for us to interface the microcontroller with potentiometer. How do we interface it? Please refer the diagram that we have given, which explains the connection details. The first pin of the potentiometer has to be connected to the 5-volt pin of Arduino. The third pin of the potentiometer has to be connected to the ground. The middle pin, which is data, has to be connected to the A0 pin of Arduino Uno. Once it is done, time has come for us to code it. Potentiometer is attached to the A0 pin of Arduino. The sensor value is the variable that we have used that can hold the value that we are reading it through the sensor. And we have got one more important point, that is achieved through the pin mode function. Pin mode is used to declare A0 as input port. We have also used analog read function which continuously reads the data from the potentiometer. Serial.println is another function that we use for printing the content onto the serial monitor. It is just like printf statement in your C programming. Let's go through the code quickly. Int potentiometer is assigned to A0. We have initialized the potentiometer. The next step, we have got a variable by name sensor underscore value, and we have used this variable to hold the sensor read value. We've got two parts of the code, setup and loop. In setup, we have set up the baud rate as well as we are declaring the A0 pin as input port. Coming to the loop, we are reading continuously the data from the potentiometer using analog read function, and it is assigned to the sensor value. After reading it, we got to display it to the serial monitor, and we are doing it through serial.println. We have got a moderate delay there, just not to overload and for you to see it correctly. It is time for the demo now. Hope you understand the demo clearly. In this demo, we will understand how exactly to interface potentiometer with Arduino. The setup is very simple and follow our instructions as we have given during the theoretical explanation about the connections to interface the Arduino Uno with potentiometer. The potentiometer we have chosen here is 4.7K potentiometer, and a potentiometer is nothing but a variable resistor. Remember it, it is a variable resistor. Once the connections are all made, please go ahead with the Arduino IDE with our code available there. Select the appropriate COM port from the tools option. Select the COM port properly, and once it is all done, you are all set to go. Upload the code. The code gets uploaded after compilation, and once it is done, please open the serial monitor for you to visualize the output. Now you can see that the initial potentiometer values are presented as 930, 931. It settles down slowly and it is mostly 930. Now you can see that I'm having a screwdriver in hand and I'm going to rotate the potentiometer in clockwise direction. As I tune it in the clockwise direction, you can see that the values are getting decremented step by step, and that's what you are visualizing in front of you. It has come to 880 now, and when I keep rotating it in the clockwise direction, the value keeps decreasing. And that's what is the exercise that we are doing. Now, I am incrementing it. I mean, I'm rotating it in the anti-clockwise direction, and you can see that the values are incrementing gradually. That is it. You have interfaced potentiometer with Arduino Uno.